So we'll move to the two last presentations. So the next presentation is by Professor Beyer from EPFL in Lausanne on masonry buildings. So Professor Beyer,
good morning, everybody.
The floor is yours.
Okay, then thank you very much for the introduction, Professor Sambla, and thank you very much, Professor Bento, for the organization of these webinars. So I have the pleasure of talking about the chapter for the masonry buildings. If you recall, the first generation of the Eurocode 8 had a very short chapter on masonry buildings. It was 7 pages long. And most of the factors or the parameters actually in there were NDPs, including also the behavior factor, which was an NDP. Recommended values for were the following that are given here. So for unreinforced masonry buildings, for example, Q values between 1.5 and 2.5 were recommended. However, most countries adopted really the lower bound values, so 1.5. And this means basically the design was essentially based on elastic behavior of the structure. And most probably that choice was really sort of fostered by the pictures that we see after every earthquake, where really most of the damage is always concentrated in unreinforced masonry buildings, and we see pictures like the one here from Amatrice. However, at the same time, if we look a little bit closer at the damage, we see that really these very heavy damaged buildings are often historical masonry buildings, and the modern masonry buildings, they behaved actually rather well in many of the past earthquakes, in particular in many of the past Italian earthquakes, and there are several reconnaissance reports in that regard. So what is the big difference between these modern masonry buildings and these historical masonry buildings? One key feature is really sort of the absence of the box behavior that we have typically in historical buildings. And you see here a historical building which had been retrofitted at the top with a reinforced concrete slab or roof, and a ring beam. So there we have that box behavior, but then in the first floor level, we clearly don't have it. And you see really sort of the structure falling apart. So I find this picture really illustrates very well what a box behavior is. The second important feature is really the stiff floors and very good wall slab connections that we typically find in modern unreinforced masonry buildings. So if we don't have it, like in historical stone masonry structures often, then this really fosters out of plane failure of the walls, because then also the out of plane inertia forces cannot be really redistributed to the in-plane in-plane loaded walls. Plus these diaphragms don't really provide a good restraint to the out-of-plane behavior. So in modern unreinforced masonry buildings, we can really sort of say that typically we can achieve a box behavior, and this is the required characteristics are really good wall slab and wall connections and floor diaphragms with a certain shear stiffness. And that really results in the behavior that we have. First, we enable a redistribution of the forces between in-plane loaded walls, so that increases the redundancy of the system. We improve the out-of-plane stability of the walls by these good wall slab connections, and we can transfer then these inertial forces from the out-of-plane loaded walls to the in-plane loaded walls. And finally, we can really basically transfer the inertial forces to the foundation as in-plane forces in walls. So if we sum up what is basically the development after 2004, we have these observations that really document the good behavior of modern unreinforced masonry, of many modern unreinforced masonry buildings after earthquakes due to the box behavior. In addition, we have also now a whole new range of shear compression test data on unreinforced masonry walls. We have set up a European database on shear compression tests for that purpose. We also have new shake table test data on unreinforced masonry building, and we have really significant new research on Q factors for unreinforced masonry building, in particular by the research group from the University of Pavia and the research group from the RWTH Aachen. So the goals of the revision for the masonry chapter were really the formal brief, and as a particular brief for the masonry chapter was really to reduce the number of NDPs, and basically additional goals for my personal motivation was really to clearly aim for a robust structural behavior through the box behavior, really favoring redundancy, and also by limiting the axial load ratio. Why? Because we clearly see that high axial load ratios can really favor brittle behaviors or reduce the displacement capacity of our elements, and in particular also reduce basically the sort of margin of displacement capacity that we have after reaching the ultimate drift capacity and then really axial load failure. One of the key things was, of course, to update the Q factors based on the new findings from experimental and numerical studies. And my personal goal was also to provide as much background information as I could. So the scope of the chapter 14 is really modern unreinforced masonry buildings. So stone masonry buildings are not covered. These are covered in part 3 of the Eurocode, which was spearheaded by Professor D'Agostino. Then reinforced masonry and confined masonry buildings. Not covered are masonry infills, which were covered in chapter 7.4 that already Professor Beyer presented this morning. This here is the structure of the chapter, but in this presentation, I really will focus on these first few points here, and in particular on the behavior factors. So masonry buildings can be basically designed for 2 ductility classes, either DC1 or DC2. DC3 is not possible because sort of classical design capacity concepts cannot be applied to unreinforced masonry structures. So if the reference vector acceleration is smaller than 3 meters per second square, you can use DC1 or DC2. If it's larger, then DC2 is required. DC1, so here flexible diaphragms are allowed, and that of course means that we have no effective redistribution of forces from one wall plane to another, and that means a reduced redundancy. And we also have no limit on the axial load ratio, and as I said before, that has potentially effects on the wall behavior in terms of brittleness. So DC1, as you know, only the overstrength is considered, and here the behavior factor for in-plane analysis remains at Q equal to 1.5. For DC2, we have no criterion for the global mechanism. We control basically the deformation capacity by limiting the maximum axial load ratio in the masonry walls. And then we have a behavior factor for the in-plane analysis, which is a function of the structural configuration, more specifically a function of the number of walls and the coupling effect. I will come back to that in a moment, the masonry type and the axial load ratio. So as you now have seen several times in the new Eurocode, the behavior factor is written as a product of these 3 factors here, so of which are functions of the deformation capacity, the redistribution of forces, and all other sources. So now I will show you how this behavior is basically given for the in-plane analysis of unreinforced masonry buildings. And it's basically tabulated in this table here. And generally, basically, the table depends on the masonry type and the building configuration. But let's look at that a little bit more in detail. So, for example, here we have the masonry types. So masonry types are unreinforced masonry in general, then also some specific brick types, confined masonry, and reinforced masonry types. Reinforced masonry. And that, of course, is related to the deformation capacity of masonry elements. Of masonry buildings. So let's just briefly look at how the deformation capacity of masonry is typically determined. So in a building like the one that you see here on the left, we typically take then a story high element and test it in order to determine really the deformation capacity of the masonry wall. So from that, we then get basically the drift capacity, which is determined as the ultimate drift capacity, which is determined as a drift at 20% drift, 20% drop on strength. And it depends in particular, of course, also on the axial force, which is typically kept constant in the test, and of course also on the shear span, which is also typically kept constant. So from all these tests that were conducted, we set up a European database on the shear compression tests. These are quasi-static cyclic tests. And this is really a joint effort from the University of Behaviour, in particular Andrea Penna, from ZAC in Slovenia, in particular Matthias Gams and EPFL, and so us. And for modern brick masonry, so in that database, we have modern brick masonry and historical stone masonry walls, but of course here it was of interest is, of course, mainly the modern brick masonry part. So here I just give you some examples of numbers of tests that are included in the database. And of course, a lot of effort really went into investigating what are the parameters that influence the ultimate drift capacity. So here I just give you a very short overview on what we found. Also, of course, based on much research that had been conducted in the past. That is, of course, the failure mode, the shear span, the axial load ratio, the brick type, and also the wall size. If you're interested in much more background in that, then I draw your attention to that background to that report that is linked here. And based on that, we basically tabulated the ultimate drift capacity for shear failure that you see here in the left. The ultimate drift capacity is, however, not necessarily exactly the same as the drift capacity as near collapse or significant damage. And basically, to transform it, it now really depends a lot also, of course, on engineering judgment. We wanted to account for a few factors, and I name here the three most important ones. The one is really also the difference between ultimate drift and collapse drift. And so basically, what is that margin that we have after the ultimate drift? Another rather important one is also the load history effects. We know that in most of these quasi-static cyclic tests that have been conducted in the past, many more cycles have been applied in the tests than real buildings would really see in real earthquakes. And then, of course, also we wanted to derive a partial safety factor to basically move from the median value then to the 5 percentile value. All these arguments for this transformation, and then also the transformation into the Q factors, you find in that background document that is mentioned here in the bottom, that is co-authored by Guido Margenis. Now, in order to basically transfer from the drift capacity values to the QD values, we had to also, again, make some assumptions. And the key assumption here really is that the displacement capacity of the building is controlled by walls failing and shear subjected to double bending. For the two research groups in Pavia and RWT Aachen, they had carried out studies basically on seeing what is should be the QD value if the shear drift capacity is 0.3%. And so the median value is around 2. And then we basically scaled for the various drift capacities that we found for the masonry typologies, then the Q factor linearly. So with that, we had basically our QD factors. For the QR factor, so now we come to the QR factor, and then at the table, you basically find that the criteria for the choice of the QR factor here. So for in that first column, so here, for example, it says if the structure configuration has at least 6 volts of various lengths and a significant coupling effect, then you have this QR factor of 1.4. Or if you have less than 6 volts and but you have volts of various length and axial load ratios, but no significant coupling effect, then you choose this QR factor here. So why are these where are these terms various lengths, axial load ratio, and significant coupling coming from? So let's quickly look at that. So with a significant coupling, we really mean the coupling that is provided either by spandrels, ring beams, or also, of course, by concrete slabs that really act like slabs and not just as diaphragms. And there we can really clearly see that we get a significant increase in strength when compared to walls. If you basically just model a diaphragm action of these floors. In order, however, to get such a significant coupling effect, it's really necessary, of course, to have more than one story. With one story, this coupling effect is very limited. And basically, to judge whether we have a significant coupling effect or not, you can basically model the coupling effect and not model it, and then the difference in stiffness should be at least 1.5. Or the ratio in stiffness should be at least 1.5. Just here a comment, of course, in the code, we know basically in the modeling provisions, we say, so you may model the coupling effect explicitly or not. in both cases, really that QR factor is quite significant. Once, if you don't model it, then you have really the difference between uncoupled walls and coupled walls. But also, if you model really the coupled walls, there's quite a big difference between the limit of elastic behavior and really the final capacity of that structure, just because we have really a redistribution of the axial forces as well. And then we have so that the limit of the elastic behavior is really quite early on. So this is with regard to the coupling effect. And then, of course, also as in any other structure as well, the difference in wall length has an effect on the limit of the elastic behavior and that reserve capacity until really both walls are yielding. This is not any different to, for example, concrete walls. Now, really to derive these QR factors, again, it's based on studies by Morandi et al. And Butenweg, who analyzed really a large set of reference buildings. So basically, I tried then to translate this into these simple rules that you see in the table. So clearly we see it depends on, so they find QR factors between 1 and 2, depending on the number of walls in one direction, the framing action provided by slabs and beams, so this coupling and spandrels, and this coupling effect that we just talked about, and the difference in wall lengths. So here just some summary results of based on the data by Butenweg, and basically based on that we come up with these criteria. So basically you have 3 effects: framing action, the coupling effect, the number of walls and wall lengths. And
so I'm in a meeting.
Sorry?
Okay, bye.
Could you please shut your microphone, Mr. Butenweg?
Yes, sorry.
Thank you.
Okay. So based on that, we have basically 3 criterion, and if all effects are fulfilled, you can assume QR equal to 1.6. If 2 effects, 1.3, and in all other cases, it's 1. Then we have the last factor, QS, and actually for all other materials, there's basically no point talking about it because all other materials just assume 1.5. And the main source, of course, there's really the safety factors and the material properties. However, unreinforced masonry is really different because the resistance results really to a large extent also from the axial force, and we cannot assume that we have 50% sort of reserve in the axial force, of course. The material properties have a much smaller effect on the resistance in unreinforced masonry, therefore, than in other material properties. So here just some equations for flexural failure and shear failure, where you see in both cases that it's really heavily dependent on the axial force. So based on that, you can really argue that QS should be smaller for masonry than for other materials. Of course, we still, so all our design is really focused on walls failing in shear, and in shear, walls failing in shear, we have also that part of the cohesion from in the resistance. So we have a partial safety factor on the cohesion. In addition, we might have some effects that are not modeled, like flange effects, but of course, this can also advance with time. So based on that, we assume that we might have a QS factor of 1.35. I think this is really more, a generous estimate, but it's smaller than 1.5, and it might be in that order. So, but in order to be in line with other materials, we basically increase QS from 1.35 to 1.5, but in return, we reduce the QR factor from these factors that I just presented before. So 1, 1.3, 1.6 to 1, 1.2, 1.4. And this is really the background for this table that I showed you here in the beginning. The maximum Q factor was, however, so the final Q factor is, of course, the multiplication of these 3 factors, but the maximum Q factor was kept at 2.8, and that was really to be consistent with reinforced concrete structures. Reinforced concrete wall structures, depending on the degree of coupling, had Q factors between 2 and 2.5 for DC2. So maybe the Q factors that we have here, as a first impression, they might seem high, but in fact, one should also keep in mind that unreinforced masonry structures, they have typically a higher redundancy than reinforced concrete wall structures, and the coupling plays a larger role. So they have a stronger coupling effect typically than reinforced concrete wall structures. So that is really taken as a justification of these higher Q factors for some of the masonry typologies only. So this was about the Q factors for the in-plane behavior. So now let's also briefly look at the behavior factors for the out-of-plane response. So we look here. So for DC1, for all masonry typologies, we have a Q factor for the out-of-plane response of 1.0. For DC2, it depends on the masonry typology. For so unreinforced masonry, we have Q equal to 1.25, for confined masonry as well, and for reinforced masonry 1.5. However, in fact, it is not necessary that explicit checks for the out-of-plane response are done if the slenderness limits that are given in the code are met. And again, there's a background document on these out-of-plane limits available. So to close with my presentation, I really just want to draw your attention to some to the background documents that are all openly available on Zenodo, so that data repository from CERN, and often so whenever it was appropriate, we basically don't just share the code, the text, but also the data and the code that underlies basically the analysis with which we derive the conclusion. So, for example, for the drift capacity models, you find in there all the shear compression test data, and also all the code for analyzing this data. Before I close, I really want to acknowledge, in particular, quite a few people, in particular, of course, my collaborators who helped me developing the work, but also in particular the colleagues from the University of Pavia, so Professor Guido Magenes, Dr. Paolo Morandi, and Professor Andrea Penna. A lot of the revisions are based on the work, as well as, of course, on the colleagues from the RWTH Aachen, so in particular, Professor Christoph Butenweg. And I would also like to mention Dr. Matthias Gamm from ZAG, who was really also one of the driving forces behind it, the open database for the shear compression test. I would also like to acknowledge the fruitful discussions that we had in the working group 1, Masonry, the project team 2, in particular Professor André Blimier, Professor Philippe Bisch, and Professor Dina Dayala for editing the final version of the code. With that, I'm at the end of my presentation. I thank you for your attention.
Thank you very much, Professor Beyer. We have a question from Francesco Mesali from TU Delft. He mentioned that probably in slide 34, the friction coefficient is maintained equal to 0.4.
Yes.
And in several experimental campaigns, higher values were found. So his question is, what was not considered the opportunity to revise such a value?
Well, I mean, the resistance models are really taken from Eurocode 6. So we didn't want to revise something, but what is really sort of the domain of the Eurocode 6. So we really try to be there as consistent, or completely consistent, basically.
Okay, thank you. I have a question about the European database. So you mentioned that it mainly concerns static failure. So what are the data allowing us to account for the cyclic failure or the load history, as you mentioned also in your presentation?
Okay, so there's a quasi-static test, but they're all quasi-static cyclic tests that were considered. Okay, so the cyclic effect is considered, and the load history effect in the sense of the number of effective cycles that are applied, not in terms of the order of cycles that were applied. So there we can basically compare when we do rainflow counting on real what real buildings would be subjected to, and compare basically the number of cycles to the to the cycles that were applied in quasi-static cyclic tests, we see that that the number of cycles applied in quasi-static cycles is often really very much higher. I mean, really like often sort of a factor of 3 or something like that higher. And that, of course, is very clear. It comes from the fact that we would like to really determine the failure drift as accurately as possible in the test, and therefore we apply relatively small displacement increments. But compared to the demand that we have really in low to moderate seismic countries, this then often results really in cycles that number of cycles that are much higher than what we see. One thing that is clearly not considered when we do these quasi-static cyclic tests is really the, of course, any dynamic effects. For the moment, we assume that these are not too significant, but it's also basically our ignorance there. So this is the data that we have, that is the data on which we can base ourselves. And whenever we do, however, comparisons with shake table tests, we see that the order of magnitude of the drift capacity seems to be approximately correct, or it could potentially be a little bit higher, the drift capacities that we see in the shake table tests.
Okay, thank you. So we can move to the next presentation. Thank you very much, Professor Beyer.